Howdy! Welcome to Aspire Mountain Academy. I'm Professor Curtis, your instructor for this course in Introductory Statistics. In less than 10 minutes, this video describes the requirements and the test statistic used when conducting a hypothesis test on population proportions. Let's get started. Okay, first off, there's some requirements that need to be met because the methodology that we're using for conducting hypothesis testing on proportions is based on certain assumptions, and that's where these requirements come from. So first of all, we need to have sample observations that are simple random samples. Second, we need to have the conditions for the binomial distribution satisfied. And third, we need to make sure that the number of failures and the number of successes in our sample is each greater than or equal to 5. We got to have at least 5 of each. And the reason for this requirement is so that we can then, have the normal distribution as an approximation for the binomial distribution, because that was the second requirement. If the conditions for the binomial distribution are satisfied, then we should be able to use the binomial distribution. But we've got some extra tools in our toolbox for normal distributions that we don't have for other distributions. So we really want to use the normal distribution, and we can approximate that if we have at least 5 failures and 5 successes. Note that the lowercase letter p is what we're using for the proportion in the population. The sample proportion is represented with p hat. Let's take a look at our test statistic. We saw in an earlier mini lecture a table of the test statistics that are used for hypothesis testing on various population parameters. Here's the test statistic equation for the hypothesis testing on proportion. So notice we're calculating a z-score here, and that's going to be our test statistic, and we calculate it by taking the p hat, which is the sample proportion, okay, and then we're going to subtract from it the population proportion, and then we're going to divide it by the square root of that same population proportion multiplied by the complement. Okay, so you can think of P and Q as proportion of success and failure, because we remember, have that requirement for the binomial distribution. And then we're just dividing it by the sample size. So these are the different elements that we have in our test statistic. Let's look at an example problem that we're going to be using in this and future mini lectures. So here we have information from the National Cybersecurity Alliance that says 93% of computer owners believe they have antivirus programs installed on their computer. We have a random sample of 400 scanned computers. We found that 380 of them actually have antivirus software programs. So now we're asked to answer a few questions. First, are the requirements for conducting the hypothesis test met? What are the null and alternative hypotheses? Will our hypothesis test be a one-tail or a two-tail test? And what is the value of the test statistic? So we can answer these questions based on what we've already discussed in this mini lecture. Start off with, we need to check our requirements are met. That's the first question we were asked. So the sample observations are simple random samples. We don't have any information that would indicate otherwise, so we just go ahead and say that's been met. The conditions for a binomial distribution are satisfied. I mean, everything's either a success or a failure. Either you have the antivirus program on the computer or you don't. So it's one or the other. Everything is independent. So just because one computer has antivirus, it's not going to say whether or not any other computer has antivirus program installed. And then, we've got, plenty of samples in our sample size. So we have the conditions for the binomial distribution satisfied. And then if we look at the number of successes, the number of failures, we've got way more than 5 in each case. So we have our requirements met. Looking at the hypothesis test itself, so the original claim that 93% of computers have antivirus software, we can express that with the lowercase letter p equal to 0.93. Okay, this is then going to be the null hypothesis. Well, it can't also be the claim. It has to be the null hypothesis because it's got any semblance of equality goes with the null hypothesis. So then the claim, we have to take the complement of that to get the alternative. So the alternative here is going to be that the proportion is not equal to 93%. And of course, because we have the not equal to sign there, that means we're going to have a two-tailed test. Right? So there we've got the next set of questions answered. So we've got a little bit more to go. We can actually select a significance level. It didn't give us one, so we're just going to assume that we're going to take 5% for our alpha. That's by far and large the most commonly selected value. And so the sample statistic that's relevant for population proportions is going to be the sample proportion. Remember, the proportion is an unbiased estimator, so we're going to use the sample statistic to target the population parameter. And in this case, that's going to be p hat. So p hat is going to target little p. We can calculate our test statistic by applying our formula. So there's that equation that we saw earlier. We plug in the values that we have. We know there are 380 computers that have the antivirus software installed out of 400. The claim is 93%, so that's going to go in for P. And then, of course, Q is going to be the complement of that, so we just subtract that from 1 to get 0.07. And then, again, sample size is 400. We punch all this out on the calculator, and out comes 1.57. That then is our test statistic. And that brings us to the end of this mini lecture. I hope you found it helpful. You can find more mini lectures for this and other courses at AspireMountainAcademy.com. Thanks for watching. I'll see you in the next video.